Atomic numbers and atomic mass number. The number of protons in the nucleus is chemically identity of an element. This number is called atomic number, Z of the element. The positive charge on the nucleus is due to the protons present in it. Positive Ze. Atoms being electrically neutral, it contains the same number of extranuclear electrons in it as its atomic number. Therefore, the total electronic charge on an atom is minus Ze. Thus, in any atoms. Atomic number Z. Number of protons is equal to number of electrons. As can be seen from table 4.1, mass of an electron is negligibly small compared to that of the nucleons. As a result, the mass of an atom can be considered to be concentrated in its nucleus. The approximate mass of one proton or one neutron is 1 U. Therefore, approximate mass approximate atomic mass is Dalton's is numerically equal to the number of nucleons in the atoms. The number of neutrons in the nucleus is designated by the symbol capital N, and the total number of protons and neutrons, that is nucleon, in an atom is called its atomic mass number capital A. Mass number capital A is equal to proton number Z plus neutron number N. Therefore, A is equal to Z plus N. N is equal to A minus Z. The composition of any atom is represented by element symbol X with the atomic mass number capital A as superscript on left and atomic number Z as subscript on left. AZX. The atom or nucleus having a unique composition as specified by AZX is called nuclide. Problem 4.1. Find out the number of proton, electron and neutron in the nuclide. 40, 18 argons. Solution. In case of the nuclide 14, 18 argon, atomic mass number is equal to 40. Atomic number is equal to 18. Number of protons is equal to number of electrons. Z is equal to 18. And number of neutron N is equal to A minus Z. 40 minus 18 equal to 22. 4.3. Isotopes, isobars and isotones. Similarity in composition of nuclide results in three types of relationships. First, isotopes. Some elements exist as single natural nuclide, for example, 19 fluorine 9. However, many elements exist naturally as mixture of two or more type of atoms or nuclei. These individual nuclides are called isotopes of that elements. All the isotopes of an element have the same number of protons but different number of neutrons in their nuclei. As the proton number is the atomic number, all the isotopes of an element have the same position in the modern periodic table and exhibit similar chemical properties. All the natural isotopes of an element coexist and have a definite natural abundance. Table 4.2 show various features of the three common isotopes of carbon. Second, isobars. The atom of different element having the same mass number but different atomic number are called isobars. The isobar are different elements. They have different chemical properties and occupy different position in modern periodic table. Table 4.3 show an illustration of isobars. 4.2. The two natural isotopes of chlorine, 35 chlorine 17 and 37 chlorine 17, exist in relative abundance of 3 is to 1. Find out the average atomic mass of chlorine solution from the relative abundance 3 is to 1. It is understood that out of 4 chlorine atoms, 3 atoms have mass 37 and 1 has mass 37. Therefore, the average atomic mass of chlorine is equal to 3 multiplied by 35 plus 1 multiplied by 37 upon 4 is equal to 35.5. 4.2. Isotopes of carbons. Symbol 12 carbon 6 or C carb 12. Atomic number is Z 6. Atomic mass number is 12. Neutron number N is A minus Z. 12 minus 6 is 6. Percentage abundance is 98.9%. Stability is stable. 13 carbon 6 or carbon 13. Atomic number is 6. Atomic mass number is 13. Neutron number is N is equal to A minus Z 7. Percentage abundance is 1.1%. Stability is stable. 14 carbon or carbon 14. Atomic number is 6. Atomic mass number A is 14. Neutron number N is A minus Z 8. Percentage abundance is smaller than 0.00017 percentage. Stability is radioactive. Isobars 14 carbon 6. Atomic number Z is 6. Mass number is 14. Number of proton Z is 6. Number of neutrons N is 8. 14 nitrogen 7. Atomic number Z is 7. Mass number capital is 14. Number of proton Z is 7. Number of neutron capital N is 7. Three element Q, R and T have mass number 40. Their atoms contain 22, 21s and 20 neutrons respectively. Represent their atomic compositions with appropriate symbols. Solution is A equal to Z plus N. Z is equal to A minus N. For the given three element, A is equal to 14. Value of the atomic number Z are obtained from the given value of neutron number N using the above expression. For Q is to Z is equal to A minus N is equal to 40 minus 22 equal to 18. R is to Z is equal to A minus n is 40 minus 21 equal to 19. 40 is to z is a minus n. 40 minus 20 is equal to 20. Atomic composition of the three elements is written as follow: 40, 18q, 14 r, 19, 40 t, 20. Isotone. The atoms of different element having same number of neutrons in their nuclei are called isotone. Table 4.4. Show example of isotones. Isotones. Isotone 11, boron 5. NO number 5. Mass number A 11. Number of neutron N is equal to A minus Z. 12, 6 carbon. Atomic number Z is 6. Mass number is 12. Number of neutron N is equal to A minus Z. When we consider some more aspects of nuclear in chapter 13, drawback of Rutherford atomic model. Let us now go back to the point of time when Rutherford put forth his nuclear models of atoms. It is akin to a miniature of the solar system. The nucleus playing the role of the massive sun and the electrons are lighter planets. Electrons in this model could be stationary as the electrostatic force of attraction exerted would pull them towards itself, and this would form a miniature version of Thomson's atomic models. However, the electron revolving about the nucleus, as described by the Rutherford, also pose a problem. Electrons in the Rutherford models are negatively charged particles in orbital motion. Such orbital motion is an accelerated motion accompanied by a continuous change in the velocity of electron as noticed from the continuously changing directions. According to the electromagnetic theory of Maxwell, accelerated changed particle would emit electromagnetic radiations, and electrons in an orbit would emit radiations. Equivalent energy possessed by the radiation associated by the electronic motion, the orbit would therefore shrink continuously. Thus, an electrons orbiting about the nucleus will follow a spiral path to the nucleus. It can be seen that the Rutherford atomic model has an intrinsic instability of atom. However, real atoms are stable. Second, the second serious drawback of Rutherford model is that it does not describe the distribution of electrons around the nucleus and their energies. The drawback of the Rutherford models were overcome in the Bohr atomic models.